In this lesson, we will learn about the Cumulative Distribution Function, or CDF for short. Now, this function can serve as an alternative visualization to abstract insights from our underlying data. Insights that aren't immediately clear from our histogram. In particular, the Cumulative Distribution Function is a way to represent all of the percentiles of our data in a way that just isn't possible for the histogram. For instance, if I would give you a single value from your dataset and the entire histogram of the distribution, and I would ask you what the percentile was of that specific point, then that would be impossible to abstract by looking from the histogram. So what then is the CDF? What does the Cumulative Distribution Function actually represent? And as always, instead of giving you a general definition, we will learn about it by starting with an example. In this case, we have a very small dataset of 8 data points. Now, how do we get the Cumulative Distribution Function and its visualization, the plot of it, from this set of numbers? To do so, we need to go through a number of steps, but each step is quite easy. They are represented in this table right here. Now, the first column is just our dataset, not in any particular order. Then the first step that we need to do is to order our data points from small to large. And that's what's being done in the second column. We see that we go from 1.5, 2.9, all the way ever increasing to 9.9. Then the second step is to give each data point in our ordered set of data points a ranking, a number indicating its position in the list. In the third column, we see how this goes. So our first element will be rank 0, the second element will be rank 1, and all the way to the largest number, which we will give rank 7. Now, the third step is to convert these rankings into percentages. Now, this is very easily done once we know the total number of data points in our dataset. In this case, we have a small dataset of just 8 data points. Now, how we get the percentage is just dividing the rank by the total number of data points and then multiplying by 100. So we have 0 divided by 8 is 0, multiplied by 100 is 0%. 1 divided by 8 is 0.125, multiplied by 100 gives us 12.5%. 2 divided by 8 is 1/4, which corresponds to 25%, and so on and so on. Then we get to the largest number, 7 divided by 8 corresponds to 87.5%. Now note that these percentages are very similar to the percentiles we learned about in the previous lesson. Let's take, for instance, the number with rank 4 assigned to it. We see that it has a percentage of 50%. And if we then look at the amount of data points that are smaller than this number 5, then we see that there are 1, 2, 3, 4 out of 8 data points that are smaller. Therefore, 50% of data points are smaller than this number right here. And in this way, it is very similar to the percentiles that we learned in the last lesson. In fact, the more data points in our dataset, the more these percentages and the percentiles will be the same. So now the fourth step is to make this a visualization. So we want to plot these percentages and the corresponding values of our dataset onto a graph. And if we do this, then we get the familiar visualization of the Cumulative Distribution Function. And for a normal distribution, which we will see in the code in a brief while, it looks like this. Now, how do we interpret this? Well, on the x-axis, we have all of our data points. In fact, they are ordered from small to large. On the y-axis, we have these percentages, but this time just in a number, going from 0 to 1. So we have 20%, 40%, 60%, 80%, and 100%. And this is the cumulative probability. And now we can see why the Cumulative Distribution Function is extremely well fit to determine the percentile of any value that we want. For instance, let's take this value 0 right here. If we go up to the graph until we meet it, and then go to the left of it, then we end up at 0.5. And thus we conclude that the value 0 is at the 50th percentile of our data set. But also if we take this 1 for instance, and we go up and then we go to the left, then we see that it's roughly at the 90th percentile. Now because the y-axis also represents the percentiles, we can change this procedure around in order to visually discover the values that correspond to specific percentiles, but thus also to determine the bounding values for any data interval. So let's see how this works. Let's say that we want, for instance, to find the values that bound the 80% data interval. Now remember, the 80% data interval is bounded by the 10th percentile and the 90th percentile. And thus, we find the 90th percentile roughly around here between 0.8 and 1, and the 10th percentile between 0.2 and 0. Now what we do then is we trace these percentiles horizontally to our cumulative distribution function. For the 10th percentile we end up here, and for the 90th percentile we end up here. And then once we hit our CDF, we trace them down vertically, and thus we arrive at a specific value in our dataset. For the 90th percentile, we get a little bit smaller than 1, and in the case for the 10th percentile, we get a little bit larger than -1. And thus we conclude that the 80% data interval for this distribution function, and thus for this dataset, lies between roughly -1 and +1. And this we could just visually observe by looking at our CDF. So how do we now produce the cumulative distribution function for your own data? And how do we in fact plot such nice figures? Well, let's find out by looking at the code. And this brings us to the same notebook cell from the previous lesson, because there we already introduced a lot of the things that we need to make the cumulative distribution function. So we will just reuse a lot of the code to avoid any double work. Now, this first definition of this user-defined function we will need in this lesson, but only when we start plotting things. So we immediately go to generating our distributions. First, we define the number of observations in our population dataset. Then we define a mean, a variance, and a standard deviation up front. Now we will use these to generate our normal population, a normal distribution with the mean 0 and the standard deviation roughly 0.707. And the number of elements will of course be 100,000. So now that we have our normal population, we want to make the cumulative distribution function for this population, and then also plot this cumulative distribution function. And to do this, we can skip ahead, because all of this code here we just use to generate the figures of our sigma levels, and we skip ahead all the way to this portion right here, where we start generating the CDF. Now remember from our slides, the first step is to order our data, because at this point we're still stuck with just a Python array with a lot of data, not in any particular order. So the first step is to order our data. So we need a new Python array, sorted normal dist, which is a sorted array of our normal population. And this can be very easily obtained by just typing numpy.sort. And this is how easy it can be to sort a Python array of 100,000 unsorted random numbers. Going back to the slides, we see that the next step is to first give every data point a ranking and then convert this ranking into a percentage. Now what we're going to do in the code is to combine these two steps into one. We're going to assign each element in our ordered array a number between 0 and 1. And a number between 0 and 1 can of course be easily converted into percentages, for instance 0.6 being 60%. So let's see how we can do this in just one line of code. So this new Python array, which will be the empirical CDF of our normal distribution, can be obtained in the following way. We will again make use of the numpy.linspace function, which we also used in the previous lesson. Remember, what this function does is it creates a new Python array of equally spaced numbers. Now in this case, our numbers will start from 0 and end at 1. And the total amount of numbers that are equally spaced is equal to the amount of data points in our population, so n pop. So for instance, as an example, if npop is 5, then this function will return an array being 0, 0.2, 0.4, 0.6, and 0.8. So equally spaced numbers and a total size of 5. And thus at this point we have two Python arrays. We have our sorted values of our normal distribution, and we have the corresponding values between 0 and 1, representing the percentages. And it is exactly what we required to get the cumulative distribution function. We have our ordered column and the corresponding percentages. Now, because we have two arrays with corresponding elements, in the same way as we had the two columns in our table in the slides, this visual will be very easy to plot. We already defined our x2 in the previous lesson in the same notebook cell, and we just add .plot. Now this will be a line plot, so we will need an x-axis and a y-axis. For the x elements, we will just use the ordered elements of our dataset. So just all of our values of our dataset in order, from small all the way to large. Then on the y-axis, we will take the array of percentages. These correspond to the percentiles of each value. And then we just color it sky blue, and the transparency will be 0.9. And plotting this, and let me just comment out these lines briefly, we will get to them shortly, we already get the cumulative distribution function that we were looking for. It's this, for a normal distribution, this very familiar smooth curve like this. And the same insights, of course, apply. Now, what were the other lines that I commented out? Now, because in this case, we are working with a population dataset that is generated from a perfect normal distribution, we can use built-in Python functions to generate a theoretical cumulative distribution function. In fact, in the same way that in the previous lesson, we defined a theoretical probability distribution function that approximated our histogram. And we will here work in a very similar way. We first define a new Python array, x, which will be again a numpy.linspace. In this case, our linearly spaced elements will start from our minimum element of our normal distribution and end at our maximum element of our normal distribution. And we will take a length of 100. Then the theoretical cumulative distribution function can be easily made by the following. We have stats.norm.cdf in the same that we had before norm.pdf. And as is the case for the probability density function, which will make this nice bell-shaped curve, the cumulative distribution function also requires three parameters. This Python array that we just created, a mean of our distribution function, and a standard deviation of our underlying distribution function. And now we have again two Python arrays, our x and our theoretical CDF, and we can plot this using a line plot. Now if we do this, and we just for now comment this line out, we see that both of these functions actually overlap. Now this is because our empirical CDF was based on a population sample of 100,000 data points. And this is such a large number that the resulting curve will be very smooth. If we, for instance, change the number in our population, let's say from 100,000 to, let's say, 100 elements, then we will see that our cumulative distribution function based on these populations will be a jagged line around the smooth curve of our theoretical cumulative distribution function. Now, one last thing that we want to do is to make these shaded areas on our cumulative distribution function plot that show the connection with the percentiles and the data interval. And that is exactly what this user-defined function that I now skipped 2 times actually does. So we see that I call this function at this point. Now there are several parameters that go into this function. First of all, the axis of the figure on which we are already plotting. In this case, this axis already contains the empirical CDF and also the theoretical CDF. The second element is the Python array that contains the ordered set of all of our data points of our population distribution. The third parameter is the theoretical cumulative distribution function, and the fourth and fifth parameter are two percentiles. In fact, these are the percentiles on which we want to draw these lines. And remember that these specific percentiles delineate the 80% data interval. Now, how this function works and how all of these parameters that we give it result in this nice figure with shaded areas and lines is described by this code in this function. Now, I won't go into this code in these lectures. Of course, as always, I refer you to the corresponding video on the Code for Data Science YouTube channel that belongs to this course. If we just run this cell and see what this function does, then we indeed see that we get the plot that we had in our slides. We see a theoretical cumulative distribution function and the empirical one below it, but they perfectly overlap. And then we see that for the 10th and the 90th percentile, we have horizontal lines that cross our distribution function and then go down to the corresponding value in our population sample. And this concludes these couple of lessons on the normal distribution. And in fact, this will be all that we will learn in this course about the normal distribution. Now, in the next lesson, we will explore different types of distribution functions. And with the tools at your disposal now, the probability density function, the histogram, the cumulative distribution function, percentiles, data intervals, and so on, all of these tools will make you more able to abstract insights and appreciate these new types of distributions. So I will see you in the next lesson.